When physicists look at the world, they are constantly measuring properties of matter, but there is a crucial hurdle. We have to figure out if a measurement describes the specific, random lump of stuff sitting on the table, or if it defines the universal identity of the substance itself. To solve this, we can run a simple test. Imagine a sealed container filled with a gas. Now, picture taking a microscopic razor blade and perfectly slicing that container straight down the middle, splitting the system into two equal isolated halves. In this split container, mass and volume in each half drop by exactly 50%. These measure the physical amount of stuff. But temperature and pressure remain identical to the original box. Both halves sit at exactly 80 degrees. They completely ignore the division. This mathematical consistency provides the fundamental test for how we classify every physical attribute in thermodynamics. By observing how a property reacts to being split, we can distinguish between measurements that track the total size of a sample and those that define its intrinsic physical state. Properties that care about the size of our system are called extensive variables. They scale directly with the physical extent of the object you are measuring. If you take a mug of hot coffee, pour it into a pot, and add a second identical mug, the properties simply add up. You now have twice the mass, twice the volume, and twice the total internal energy stored in the liquid. The properties that ignore size are called intensive variables. These describe the nature of the substance itself, completely independent of how much of it you happen to have in the room. You could pull a single microscopic drop of coffee out of that massive pot, and that tiny drop will still register the exact same temperature and atmospheric pressure as the entire batch. It's easy to assume a massive pot of liquid must somehow carry a higher temperature than a tiny mug, just by virtue of being larger. But temperature describes the average kinetic energy of the molecules, not how many molecules are moving. We use extensive properties to run a total inventory of a system's size, while intensive properties dictate the exact local physical state of the material. Knowing this division allows engineers to perform a highly specific mathematical trick. If you take one extensive property and divide it by another, you isolate hidden universal constants. Let's test this on a solid block of aluminum. We start by taking the total mass of the block and dividing it by its total volume. Dividing the extensive mass cube by the volume grid cancels the size variables, collapsing into a new intensive property, density. Scaling up to a 1-ton slab doubles mass and volume equally. The ratio stays identical, leaving density completely unaffected. We apply this exact same ratio technique to engineer other vital metrics. Dividing total mass by the number of moles gives us molar mass. Dividing total internal energy by volume gives us the internal energy density of a space. This art of the ratio is how chemists and engineers consistently cut through the noise of arbitrary, messy, real-world samples to extract universal laws they can actually build with. All of these properties eventually feed into a single mathematical statement. For a simple physical system, everything is governed by what we call the fundamental thermodynamic relation. This equation calculates the change in a system's total internal energy. Notice how it is structured as a sum of distinct terms. We have the intensive variables, temperature, pressure, and chemical potential, highlighted in one color. Then we have our extensive variables, entropy, volume, and number of particles, in another. Every term perfectly pairs an intensive potential that drives a change with an extensive amount that receives it. Temperature drives the flow of entropy. Pressure drives a change in volume. Predicting how any system will behave requires mapping out this exact interplay between the local potentials pushing for a change and the total physical content resisting it. Up to this point, our entire logical structure has relied on a quiet underlying assumption, additivity. We assume that combining two systems always yields the exact sum of their parts. But if we push to the extreme edges of scale, that assumption fails. Watch what happens to this shrinking material. As we scale a piece of tin down to a nanometer-sized particle, the energy of the outer surface atoms overwhelms the bulk volume inside. Because the surface-to-volume ratio is now enormous, a strictly intensive property like the melting point drops. It becomes dependent on the size of the particle. We see similar breakdowns when we zoom out to the cosmic scale. Once long-range forces like gravity enter the picture, the neat additive math of total energy breaks down. Every particle is now pulling on every other particle across vast distances. This image captures turbulent, star-forming gas. When a protostellar cloud like this collapses, it interacts with its own gravitational field, resulting in a bizarre, non-extensive behavior known as negative heat capacity. As the cloud radiates energy into space and loses heat, it contracts, and the resulting gravitational squeeze actually causes its core to grow hotter. Black holes present an even more radical departure from standard extensive behavior. In this image of a supermassive black hole, we see that entropy scales with the surface area of the event horizon rather than volume. Because entropy here grows with the square of the mass, merging two black holes results in a final entropy that is double the sum of the original two. The clean division of extensive and intensive properties perfectly organizes the everyday reality we live in. But analyzing the exact points where this division shatters is what points physicists toward the most profound mysteries left in the universe.